welcome to today's lesson. We are going to focus on understanding multiplication of whole numbers. And we are going to look at the different solution paths to multiplying 49 times 25. The most common path is the standard algorithm, as you can see on this screen. But the big question is, how does it work? So the methods we are going to focus on will somehow try to unpack the standard algorithm, and we'll be in a position to understand why this method works. So thinking about 49 times 25, we are going to see the role that place value plays when it comes to understanding multiplication of whole numbers. 49 can be decomposed to 40 plus 9 multiplied by 20 plus 5. When we unpack 49 to read as 9 ones and 4 tens, which is 40, we actually emphasize the role of place value in the respective digits. We no longer see the 4 as simply 4, but the 4 is the 4 tens. And the same case applies to, we no longer see 2, but we see 2 tens. So when it comes now to multiplication, with the main focus being on the role of the place value, we can be able to see our path number 2 as something we call use of partial products in multiplication. In this case, I want to use something very visual or illustrative, and I want to use a little box. And my box is going to be partitioned into 4 little sections so that they can correspond with the 4 places or the 4 parts of my digits, the 4 parts of my digits. So we have 40 plus 9, the 40 will go there, and the 9 will go there. The 20 will go there, and the 5 will go there. We are going to multiply 2 numbers at a time, one along the column and its corresponding number along the row. And each of these little sections, we are going to place our partial products. So let's go. So we have 40 times 20. So for this little section here, we are going to have the partial product for 40 times 20, and that is going to be 800. The other little section here, we are going to have 20 times 9, which is 180, 40 times 5, which is 200, and 5 times 9, which is 45. So to get the final answer, we are going to add all these partial products, and we make sure that we match the digits with their corresponding place value positions. So when we add, we are going to find that we get the same solution as we found or as given for the standard algorithm. So I don't know whether you see any correlation or any relationship between the partial products we have gotten here and the products that are obtained above here. So if we look at this, we can tell that 200 plus 45 is the 245, and 800 plus 180 is the 980. Now, thinking about the same question, we can think of our path number 3, and we'll still treat our multiplication by use of the partial product. And in this case is, if you are to organize or to think through the standard algorithm, just the way we multiply, instead of multiplying 9 times 5, we have 45, we write a 5 and we hold 4 in our hands. How about just writing the partial product as we multiply and we take care of the place value? So in this case, we have 9 times 5, we have 45, we write it down, which is 4 tens, 5 ones. And then we come to 4. This is not just 4, but it's 4 tens times 5, giving us 200. And then we come to 9 times, this is not just a 2, but it's 2 tens. So 2 tens is 20. So 9 times 20 is 180. And then we have 4 tens. This is actually 4 is at the place, at the tens place, and 2 is at the tens place. So this is 4 tens times 2 tens, giving us 40 times 20, 800. When we add this, we can see they correlate to what all the partial products we got at the path number 2, and we get the same solution. So the other path is along the same line, something we call distributive property in application. And we are talking of 40 plus 9 multiplied by 20 plus 5. So how do we distribute these? So we have every number in the first parenthesis will multiply every number in the second parenthesis. So we have 40 multiplying 20, and we have 40 multiplying 5. So we can talk of this being the first product, this one being the second product, and then we can talk of 9 multiplying 20 and 9 multiplying 5. This is the third product, and this is the fourth product. So with that, the same partial products we've just talked about, and if we focus on the first product, it will be 40 times 20, giving us 800. The second product is 40 times 5, giving us 200. And the third product will be 9 times 20, giving us 180. And 9 times 5, giving us 45. We get the same partial product. And when added, we have the same solution, Now, do we have another solution path? Definitely there is. There is an algorithm, multiplication algorithm, an alternative one we call lattice algorithm. So lattice algorithm we can label this as our path number 5. And how different is it? By the lattice algorithm, we also draw a rectangular array or a lattice, and we draw the number of columns and the number of rows corresponding to the number of digits of the numbers being multiplied. Because we have a 2-digit number multiplied by a 2-digit number, that means we are going to partition this rectangular box into 2 columns by 2 rows. And so we show the digits corresponding with each of these columns, and the other number 25, its digit will correspond to the right with the rows that we have created. So we arrange it like that. Notice this is a little bit different, the way we have written these digits from how we did for the box here. The box, we were really keen on the place value of our digits. So instead of just writing a 4 there, we wrote 40. But in this case, for the lattice algorithm, we just indicate the digits as they were given, 4, 9, 2, 5. Now, for the lattice algorithm, we usually divide each of these little sections. We draw a diagonal. We draw a diagonal like that. And we can extend our diagonals a little bit outside, and we complete the spaces inside each of these little square that we have divided with a diagonal. So every time we multiply the corresponding digits for the row and for the row and for the column, like in this case is 9 times 2 is supposed to be 18, 1, 10, 8 ones. We always show the digits which is at the lower place value on the lower side of this diagonal, and the digit which is at the higher place value on the upper side of this diagonal. So we have 9 times 2 being 18, so we show 8 here, and we show 1 above the diagonal. 9 times 5 is 45, which is 4 tens, 5 ones. We show 5 ones at the bottom of the diagonal and 4 tens on the upper side of the diagonal. We go to 4, corresponding with the 2 for this section here. 4 times 2 is 8, 8 ones. So that means we don't have a 10, 0 tens, 8 ones. So we'll show 8 there and 0 tens. And then we have 4 times 5 is 20, which is 2 tens, 0 ones, 0 ones, 2 tens. Now, how do we find the final answer? How do we find the final answer? We add along the diagonal. And because we are dealing with our numbers, which are in base 10, our numbers, every time we make a group of 10, remember, we are to exchange that or to trade that one to a 1 in the higher place value. So each of these diagonal, each of these spaces represented by these diagonals represent the place values. They represent the place values. Like we will have ones here, we'll have tens here, we'll have hundreds here, we'll have thousands here. And that's why this algorithm works, because the diagonals actually create the respective place values. So we add whatever is inside this section along the diagonal. Like for the ones, we have a 5. For the tens, we have 8 plus 4, we get a 12, which is 110. In other words, which is, in this case, it will be 2 tens and 100, because these are 12 tens. 12 tens. So that means 10 tens become a 100. And then we remain with the 2 tens, and we move a 100, which was 10 tens, to the column respective of hundreds. Then we have 1 plus 1 is 2, 2 plus 8 is 10, 10 plus 2 is 12, and that is 12 hundredths. 12 hundredths means 2 hundredths, and then 10 hundredths. 10 hundredths is equivalent to 1,000. And whatever we have written along here gives us our final answer. So that is all. Those are the different solution paths to multiplication, and they can help us understand indeed why the standard algorithm